All right, forces of attraction. Now, this is a good section to transition from gases to liquids and solids. So before I get into any of the content for forces of attraction, which there are 3 that you will need to know, we need to make something abundantly clear. First off, the first state of matter that we have gone over in this unit are gases. There are no forces of attraction between gas particles. Why is there none? Because there's too much kinetic energy. In other words, they're moving too fast. When Derek was driving 80 miles an hour on I-4, there was this really cute girl on the side of the road, and he did not see her because he was going so fast, he didn't even have any attraction for her because he didn't really see her, again, because he was going too fast. It's hard to be attracted to something when you're going too fast, you can't even really see it. When molecules are going so fast, they can't really establish bonds between each other. They're just going too fast. However, for liquids and solids, there are forces of attraction holding them together, making the liquid and the solid. So if there are no forces of attraction between gas particles because they're moving too fast, then now let's say that the reason that there are forces of attraction between liquids and solids is because the particles are moving slowly. They're either moving slow or they are stagnant, which means they've stopped altogether. Now, you guys are sitting at a desk that's made of wood and plastic and what I can only imagine is some sort of steel. Those particles are moving. Despite the fact that they are solid, they are moving. There's only one temperature where particles absolutely stop moving, and it is 0 kinetic energy. And that temperature is called absolute zero. It is 0 Kelvin. 0 Kelvin is negative 273 degrees Celsius. We are not currently at negative 273 degrees Celsius. It's about 73 degrees in here, so I'd say that's probably somewhere in the neighborhood of 25, 26, 27, 28 degrees Celsius. You would have to get to negative 273 for all particles to stop. So even in this desk, this podium, there are still moving particles, but there are bonds. And so they're not able to move very far. Hopefully you will never experience being handcuffed. Well, if you do, you can still move. Make no mistake about it. You can move. You just can't move a lot. That's the difference between gases and liquids and solids. In a gas, you can do all this. You're free to move wherever. When you're a liquid, you can move like this. When you're solid, you can move like that. There's very little movement, but there is still movement there. And so that's going to get us to 2 prefixes that I want you all to know. And those prefixes are inter versus intra. This is a little bit of Latin for you. Inter basically means between 2 separate entities. Jade, have you ever traveled to another country before?
No.
Do you want to travel to another country? Where would you like to go?
Greece.
Okay, you want to go to Greece. Would you have to take what type of flight would you have to take in order to get to Greece? What's the name of the airport here in Tampa? It's Tampa what airport? International. You would have to take an international flight. Well, you have internation. The United States is a nation. Greece is a nation. In order to fly from United States to Greece, you have to go from nation to nation. This is known as an international flight. So we use this word all the time, international. Intermural would be like Florida playing Georgia. two separate schools. But let's say Jade wants to fly from Tampa to Chicago. Chicago is in the United States. That would be called an intra-national flight. So intra means within the same entity. When you guys go to college, let's say that you don't necessarily have what it takes to play at the actual organized athletic level. But I can tell you that if you want to be part of a club or a sorority or a fraternity, they have these things called intramural sports, where let's say Jade is going to join sorority Delta, 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 the Tri-Delts, and Kendall's going to join Zeta Tau Alpha. Those are two different sororities. They're going to have a kickball game on Tuesday nights. They always have kickball games. But they're both attending Florida State or Florida or wherever. They're within the same school. They're just competing clubs within the same school. That's called intramural sports. That's how you can make a lot of friends when you're in college. Intra simply means it's within the same school. If Jade was to go from Tampa to Chicago, that would be called an intra-national flight. If Jade was to fly from the United States to Greece, that is an international flight. So I need you to understand the difference between inter and intra. So that's where we will get started with intermolecular forces. And I want to see if you can decipher what that word means, intermolecular. So is it from one molecule to another, or is it within the same molecule? It's from one molecule to another molecule. If you have an interpersonal relationship, then you have a relationship with someone else. If you have an intrapersonal relationship, you're dealing with yourself. Okay. So intermolecular forces are forces that bond neighboring molecules to each other. And there are three that we are going to go over. If Jade and Max were to hold hands, don't hold hands. You're probably, oh, Jade's blushing. Just kidding. That would be an intermolecular bond. Let's say Jade is molecule A, Max is molecule B, and there's a bond between the two of them. That is intermolecular. But if Jade's, let's say Jade's Achilles ligament. You've heard of the Achilles ligament before. People tear it all the time. Their ACL, or not their ACL, their heel. That is what connects her calf muscle to her heel bone. That is a bond within Jade. That would be an intramolecular bond. It's something that holds her together. So there is a difference that we really need to establish here. The three that we will go over in this class today are as follows. One is called dispersion forces. Two are called dipole, dipole. I bet you can decipher that. What number is di? Yeah, it means double, so 2. And what are the two poles in chemistry? Positive and, so you got positive and negative, positive and negative. So you just interpret the language, guys. And then we have hydrogen bonds. Guess what element's involved? Helium is absolutely right. Okay, so these are the three that we will go over today. And then tomorrow we'll get into section 3. All right, so number 1, dispersion forces. Okay, I want to ask you about nonpolar bonds. Or excuse me, nonpolar molecules. Do nonpolar molecules have poles? No, I mean, that's in the name, non-polar. They don't have poles. So non-polar molecules have no poles. And when I say poles, you all must know I'm talking about positive and negative. That's what I mean by poles. When you hear polar and non-polar and all that stuff, that means there's no poles. The reason why is because there is an equal sharing of electrons. You know, typically in some social circles around our society, the person that has the most money in the group tends to be the more influential person in the group. If Colby and Max and Derek and Arshawn and David all hung out together and Colby was like the most wealthy person in the group, his words are going to have a little bit more weight than the weakest or the poorest person in the group. So we would say we have rich, we have poor. Those are polar opposites, right? Well, what if Colby and Max and Derek and Arshawn and David all made the exact same amount? Does one of them have more say than the other? Not really. Everybody's equal. So there's an equal sharing of electrons, therefore we're nonpolar. Let's go back to chemistry. Would it be nonpolar? So how is it that a polar molecule can be bonded to another polar molecule if there is no attraction there? That's where dispersion forces come in. Dispersion forces are weak forces that result in, here's a very important word, they result from a temporary, very important that you keep that in mind, temporary shift in the density of electrons in electron clouds. Okay, I want you guys to imagine that right now, all of you are equally spread throughout the room. So imagine this is a teeter-totter. It's a lever. And we have people in this class that are equally distributed across this teeter-totter. So the teeter-totter, the lever, is balanced. It's not going to tilt one way or another. It is equal. You got me? This is what we would say is nonpolar. Nonpolar is equal. But what would happen if for just a brief moment, all of you shifted to one side? Because everybody's over here. Now we have polar, which is unequal. That is what happens when we have a dispersion force. But instead of people, it's electrons. Typically, if I have a molecule of chlorine gas, take a look at those electrons. They're all equally balanced, all on the same side. That would be nonpolar. But what if, for just a moment, you had most of the electrons on one side? What would you say the charge would be on the side with all those electrons? And this is temporary. It would be negative. And so what would the side without the electrons be? That would be positive. Do you now have poles? Yes. Now you can actually form bonds. So what if there was another chlorine molecule that was in the same circumstance? Negative and positive. Are these two sides going to be attracted to each other? The positive side here and the negative side there? Yes. That is going to form a bond. Now, everyone, this right here is a molecule, and this right here is a molecule. So here's my question. is this bond I just circled in purple, is that an intermolecular force or an intramolecular force? That is, I heard intra. That's inter. This is molecule number 1. This is molecule number 2. We have 2 different molecules, and we have a bond connecting those 2 different molecules. It's like we have a flight connecting 2 different countries. Is that an international flight or an intranational flight? International. If I have molecule 1 bonded to molecule 2, that means that the bond is an intermolecular force. What would you call this bond here and here that is holding one molecule together in and of itself? That is an intramolecular. So to be clear, this bond right there and right here are intramolecular. This bond right here is intermolecular. That's the difference. And this is how dispersion forces actually happen. And this is temporary. You have to keep that in mind. This is going to be temporary.
They just all the electrons shift for a second, like by chance.
They shift by chance, and once you establish that bond, they're going to stay there until the bond is broken. They're all going to be drawn to one side. So, let's continue. When 2 molecules are in close contact, especially when they collide, the electron cloud of one molecule repels the other because negative hates negative. They repel each other. So I'm going to try to draw this. It's not going to be easy, but I think I can pull this off for you because visuals are always great. So here is an atom of chlorine. Here is its electron cloud, and this electron cloud has a negative charge. So that's what that little line means. Here comes another chlorine, guys, and its electron cloud is also negative. So how does negative react to negative? You've played with magnets before. You try to get the 2 sides with the same charge. Can you get them together? No. That's what's going to happen here. They're going to repel each other. They kind of just more or less bounce off. This is called electrostatic repulsion. However, for a moment, the electrons can shift to one side of the cloud, instigating a negative pole. And the yin to the yang of that, and as a consequence, a positive pole. So that's why I drew up above. This forms a dipole. Now, the second type of force we're going to discuss is called dipole-dipole, but those are more permanent. This is temporary. I have to make that very clear. This is temporary. They're not going to be like this for long. These dipoles are going to be temporary, okay? Remember that di means double. And pole means opposite. So you're going to have double opposite, positive and negative. Two that are the opposite from each other. So let's try another one here just to make sure that we've got this hopefully understood. Let's see, what do I want to do? Okay, let's try bromine. Bromine has 1, 2, 3, 4, 5, 6, 7 valence electrons, and another bromine is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. There's a bromine molecule. Are the electrons evenly distributed across that molecule? Sure. So this would be a nonpolar molecule. It's not going to be really attracted to anything else. But for maybe just a moment, most of the electrons are shifted to one side. That's going to cause this side to be negatively charged and this side to be positively charged. Now it can be attracted to other molecules, other dipoles. This is called a dipole. Di means double and pole means opposite. So you have two things that are the opposite of each other, the positive and the negative. And so if there was another bromine molecule that was over here that was under the exact same conditions, Max, what would the charge be of the bromine over here on the left with all the electrons? Correct. And how about the one without many electrons? Okay, very good. We have another dipole. Now, Max, yes or no? Would this positive side of this bromine molecule be attracted to the negative side of this bromine molecule? Yes, and so we have a bond. This is known as a dispersion force. And is this force intermolecular or intramolecular? This is intermolecular. Intermolecular means between neighboring molecules. Just like international is between two countries. Any questions on that? Yeah.
So when there's just a molecule, they'll shift over and that lets them deal with dispersion force.
It's the electrons orbit the nucleus, Arshan, sort of similarly to how moons orbit a planet. And every now and then you'll have more than half of those objects just on one side. And that's what happens here. The electrons are orbiting and they just happen to be collecting on one side. And that's when you can temporarily have a pole. Because that, just like moons orbit, Jupiter, for instance, has like 60 some moons. There are points in time where most of its moons are on one side of the planet. Is that going to last forever? No, they're going to go back and continue to redistribute in various ways.
How long does dispersion forces last?
Seconds. Less than that. You have to catch them when it's perfect. Okay. The second one is going to be dipole forces. At the end of today's class, I'll go over which ones are the strongest, which ones are the weakest. That tends to be a question on a semester exam review. Of the three intermolecular forces, which one is the strongest and which one is the weakest? We'll go over that at the end. Okay, so dipole just basically means double pole. That's what it means. And when we're talking about double pole, we're meaning positive and negative to positive and negative. This is the result of uneven or unequal sharing of electrons. Okay, this one is, I think, a whole lot simpler. Neighboring molecules that have dipoles orient themselves so their poles are facing the opposite poles of a neighboring molecule. All right. Max, I need your help here, just as a visual. Can you come stand up here? I'm not going to hurt you. All right. So I want you to face north. I'm going to face this way. Max, you and I need a high five. We need to face each other. Don't worry, I'll give you some hand sanitizer. So I need you to turn so that you're oriented in the way that you will face me. Okay, now we're oriented properly. And now we can high five. Perfect. Now I need you to orient to where you can wave to the person closest to you. So, can you wave you? That's how you wave? That's how I pet my dog. All right. Well, when molecules are orienting, here, molecules orient so that they can face the opposite pole. So, for instance, let's have a little before situation here. Let's have a molecule like this, positive and negative, positive and negative, negative to positive, positive to negative, negative to positive. Okay. We need to turn these around so that they can all face each other in a way that will allow them to bond with each other. Still with us, Derek? So let's do that. Let's orient these around. You guys probably cannot do this on your notes, but I'm going to do it here. Here we go. I'm going to put that right there. I'm going to put this guy right here. I'm going to put this guy, let's see. I don't know if I can turn this around. Let's see. How about right there? There we go. And I'm going to put this one over here. Okay. So we're going to make some bonds now. Right there. Positive to negative. Positive to negative. Positive to negative. And positive to negative. And then we can have positive to negative there. So what they have done is they have oriented themselves so that the opposite pole is facing, or a pole is facing the opposite pole so that they can establish a bond. If you had negative facing negative or positive facing positive, it's not going to work out. That's called electrostatic repulsion. This is called electrostatic attraction. Electrostatic attraction is when you have positive to negative. Repulsion is when you have two of the same charges. They repel each other. So these are simply dipole-dipole forces. That's what these are. Dipole-dipole. Because this molecule has two poles and this molecule has two poles. They all have two poles, but the bond between them is between two dipolar molecules. And because this is a molecule bonding one, or this is a bond connecting one molecule to another, is this intermolecular or intramolecular? And this is intermolecular. Remember, inter means between neighboring entities. Okay, and then the last one, hydrogen bonds. All right, I'm going to draw some water molecules up here to get this started. Let's see what you guys may remember. What are the large red atoms? Are those oxygens or are those hydrogens? Very good. So I'll put some O's for oxygen, and that would mean that the smaller ones are hydrogens. So let's draw some little H's in there. Very good. Okay, fantastic. Now, let's go back to more of what you should know. Which of these are partial positive charges? The hydrogens or the oxygens? If you don't know, ask yourself, what is the most electronegative element on the periodic table? F, yeah. Fluorine. Which of these two elements on the board or on the screen are closest to fluorine? Oxygen or hydrogen? So oxygen is more negative. That means hydrogen is more positive. So we're going to put this little symbol next to every hydrogen that we see. This means partial positive. Now, that means that oxygen is partial negative, but oxygen can have up to 2 bonds, but we'll just put partial negative on every oxygen. Okay. So is positive attracted to positive, negative attracted to negative, or is it positive to negative? Positive to negative. Okay, we're not to hydrogen bonds yet. I want to ask you, what type of element is oxygen? A metal or a non-metal? It's a non-metal. It's more towards the right side, and it's a gas. All gases are non-metals. What about hydrogen? What type of element is that? That is also a non-metal. It is a gas. Dead giveaway, it is a non-metal. So when you have a non-metal bonded to a non-metal, is that going to be a molecule or is that going to be a compound? A molecule. Good. What type of bonds hold a molecule together? Covalent or ionic? Okay, very good. So first part for today, or for this section, covalent bonds. Remember, sharing is caring and caring is covalent. Covalent bonds hold each water molecule together. And I mean that individually. Jade's tendons and ligaments hold jade together. Scout's tendons and ligaments hold Scout together. So this is just within one water molecule. The covalent bonds hold each water molecule together. Derek! Sorry, Scout. Didn't mean to scare you. Because, Derek, this is you. You ready? Derek, look at me. I see you. Wake up. Stand up if you need to. Get the blood flowing. Covalent bonds hold each other. They hold each water molecule together. These are going to be individual water molecules. Now, in chemistry, we represent hydrogen bonds as dotted lines. And you're simply going to go from a positive to a negative. So here's one. Positive hydrogen to negative oxygen. Here's another. Positive hydrogen to negative oxygen. Here's another. Positive hydrogen to negative oxygen. And one more. There we go. These blue dotted lines are hydrogen bonds. So let's talk about them. And let's talk about the others. So covalent bonds hold one water molecule together. So what type of bonds are the covalent bonds? Inter or intra? Intra. I heard some, David, you said inter. You said, so was that a mistake?
Well, I was looking at the covalent bonds and I saw that they were connecting the hydrogen and the oxygen. It just looks like it would be an inter since it was on the outside.
No, it's these right here are covalent bonds.
Oh, okay. Then yeah, that makes sense.
That's inter. Or sorry, you got me doing it. Intra. These are intramolecular forces. Now, the hydrogen bonds that I drew in blue hold water molecules to other water molecules. Now, a molecule that is holding on to a neighboring molecule, what is that called? Intermolecular. Okay, so let's talk about what hydrogen bonds are. A hydrogen bond is an intermolecular force. We can call them H bonds. I tell my AP Bio students this, and I'll tell you guys the same. You may use abbreviations, but if I were to walk up to you in the lunchroom or at Publix or wherever and say, Colby, what's an H bond? You're not allowed to use the word H bond. David, what does H bond mean? You can use it. You are not allowed to use abbreviations in my class if you do not know what they stand for. An H bond has hydrogen on one end and either oxygen or fluorine or nitrogen on the other end. One of those three. In the case of water, it's oxygen. Now, hydrogen bonds are the strongest of the three intermolecular forces. So that's easy enough right there. I'll tell you where the other two rank in a little bit. So let's see what you guys may know, perhaps from middle school. At what temperature does water freeze? If you have liquid water, what temperature does it freeze? 0 degrees Celsius. Anybody know what temperature it is in Fahrenheit? Okay, so it freezes at 0 degrees Celsius, which is 32 degrees Fahrenheit. Very good. What temperature does water boil? 100 degrees Celsius. And what temperature is that in Fahrenheit? Anybody know? 212 Fahrenheit. Very good. So here's why that happens. Let's talk about boiling first. If I have a water molecule, like so, and I have a neighboring water molecule over here, like so, we're going to have a hydrogen bond. Well, when you crank up the temperature with the energy up to 100 degrees Celsius, which is also 212 Fahrenheit, these bonds can no longer take that much energy. Now, the beautiful thing about hydrogen bonds is that they prevent water from it takes a lot of energy for water to change its temperature. I told you this earlier this year. You go to the beach in July, you're barefoot, you step out of your Jeep, and the asphalt in the parking lot is burning hot. You run over to the sand, burning hot. You stand on the sidewalk, burning hot. You go in the water, feels good. Because water can absorb the heat from the sun. Concrete and sand and asphalt cannot. But everything in nature has its breaking point. And when you get this water up to 100 degrees Celsius, the bonds break. And what state of matter is this water in now that they're no longer attracted to each other? And why are they not able to rebond? It's really hot, so what are they doing? They're moving way too fast. When you heat up particles, you're increasing the kinetic energy, and they're moving very, very quickly. So let's flip the script here. If you've ever steamed water on your stove, let's say that you have maybe like a ceiling or an area of a cabinet. A lot of water can condense on that cabinet because what do you think is hotter? Or let me rephrase that. What do you think is cooler? The top of the stove or that cabinet where all the steam is collecting? The cabinet. And so the water is collecting on that cabinet and it's cooler. And so the water condenses. And is there or is there not a lot of space between gas particles? There is. So what's that C word where particles are brought closer together? They're condensed. They're getting closer together. And what do we call that stage of the water cycle where water evaporates as a gas, but then it comes together as liquid up in the sky? Condensation. The reason we call it that is because you have a water molecule here, you have a water molecule here, and they move closer together and they reestablish their bonds because the upper atmosphere is very cold. And so that's going to cause the gas to condense into a liquid. And that's how rain and precipitation is formed. Now, on the other hand, let's talk about freezing. If you freeze water, you're cooling it down. is the kinetic energy going to rise or fall as the temperature drops? Fall. I mean, things just get slower when things get colder. And if things are getting slower, are the bonds between them going to become stronger or weaker? That's right. So it's a inverse proportionality here, where the slower things move, the stronger the bonds get. If I had let's see, let me find a paperclip here and do a really quick demonstration. You guys probably played with a paperclip before and you snapped it into. So I can generate some heat right now. If I got this paperclip and I unfold it and I just do this, ready? Am I generating a lot of heat by moving this slow? No. Am I generating more heat than it was when it was just sitting in that cup? Yeah. Now, watch this. Look. If you felt the tips of this, they're warm because it just generates some kinetic energy. Enough energy to break the bonds. Well, when it comes to water, you got to get it up to 100 degrees Celsius to break those bonds. So, is there a limit to how hot liquid water can get? Yes. Is there a limit to how hot water vapor can get? No. So steam can get hot enough. Water can get hot enough to burn you. You can burn yourself. You're probably not going to have the meat melt off your bones. Could steam get hot enough to just cause your flesh to ooze off your bones, really nasty? Yeah, and that because there is no limit to how hot steam can get. There is a limit to how hot water can get. That's 100 degrees Celsius. Yeah. Well, that is part of it, and so that's a good point to bring up, Arshawn. The explosion at Chernobyl, you had water, and the water vaporized because the core was so hot. What does water do when it turns to a gas? Does it condense or does it expand? It expands. Water expands as a gas, and it expands as a liquid, but even more so as a gas. And so that tank was only designed to hold liquid water, but when all the water instantly vaporized, all that gas was expanding. And think of a balloon. When balloons have too much air in them, what was the only way the air can go? Out. And that's going to rupture the walls of the container. And by the way, liquid water does expand as well. Or not liquid water, I meant to say solid water, ice. This is why around this time of year, let's say that we had some below freezing temperatures in Tampa. Do you think the pipes in Tampa, Florida are built for ice? No. And so when you have water in the pipes, they turn to ice because it just gets so cold. Ice expands and it ruptures the pipes. This is why you should never, ever put liquid water in a glass bottle and then put it in your freezer. Let's say you do that tonight. You fill an empty glass bottle with liquid water, you put it in your freezer. What do you think you're going to find in the morning? Glass everywhere. Why is it everywhere? Because ice expands. And that's how pipes shatter during this time of the year. That's how a lot of damage can be done. All right, so let's rank these as far as which one's the strongest, which one's the weakest, and then we will call it a day. So on a scale of 1, 2, 3, 1 being the strongest, it's no doubt hydrogen bonds are the strongest. No ifs, ands, or buts. When it comes to dispersion forces and dipole dipole, it's different. It depends. So I'm not going to put numbers here. It depends. For dispersion forces, they are weaker with small molecules and stronger with large molecules. The more electrons there are, the stronger they can become. For dipole dipole, it's the opposite. So when I give you your second semester exam review, and there's a question like this, it says rank the intermolecular forces from strongest to weakest. it is totally okay to say, well, you know, hydrogen bonds are the strongest, but for the other two, it depends. For dipole dipole, they're weaker with large molecules. And they're stronger with small molecules. Okay. And that's about it. So temperature definitely influences these forces on whether they're going to be in the play here. Like with hydrogen bonds, it's going to really just depend. Temperature, sea level has something to do with phase change as well and the strength of the bonds. All right. I think we're done.